So this is the third lecture in alignment of language models. In the previous two lectures, we saw how to create a reward model, how to train a reward model, how to train a policy using RLHF or different variants of RLHF. We looked at reinforced algorithm, we looked at the vanilla policy gradient, which uses the reinforced method, and finally we looked at proximal policy optimization. Today we'll look at a more intuitive way of aligning language models. So it's something that should come into your mind as without a lot of complex maths. Okay, and so it's called direct preference optimization. And if time permits, we will also look at another approach which is called distribution matching. So let's first go with this with direct preference optimization. Okay, before that, let's recall what policy gradient and PPO training objective look like. So the first step was you collect a lot of human preferences from so these outputs can come from anywhere. Okay, outputs can come from any language model or even human. Yeah, so but output can come from any language model. And based on these outputs, you learn a reward function. And why you will need a reward function? Because during the training of the policy, you will use this policy, you will use the reward function to actively label samples that come from the policy. Okay. So while learning a reward function, you're trying to find the parameters that maximize the this is the Bradley-Terry log likelihood actually. So this maximize the log likelihood of observing the correct preference pair. So this loss is very intuitive, right? It's just saying that maximize the reward of the positive sample. You have to maximize this and minimize the reward of the negative sample. That's all this loss is doing. So if you can train a reward function using directly on the preferences, can you train a policy directly on the preferences? That's what the DPO paper attempts to ask. That why do you need this intermediate step of learning a reward function before you can actually train the policy? Can you directly train the policy on top of human preferences? Because in PPO you had to do a lot of things, right? You had to learn reward function, learn value function, ensure that the gradient is within ensure that the importance weights are clipped. So you have to do a lot of things to make sure that the policy gradient works. So can we do away with that? We are given preferences and we know how to train a reward function. Can we instead directly train a policy? If I frame this question like this, that how would you go about training a policy? Does anything come to mind here? So this is a general idea of what DPO is trying to achieve. That PPO RLHF, the standard RLHF process that uses policy gradient. So what it does is that it collects preference data either from humans or using an AI, trains a reward model, and finally trains a policy using that reward model. And what DPO is trying to achieve is that given preference data, you directly train your policy. Don't have this intermediate step of reward model. That's all it's trying to achieve. Same as the same previous slide in the form of figure. Okay, so the first slide that I show you had these parameters for I, and it has parameters for the reward model and had parameters for the policy. Now consider a case where you can learn any arbitrary reward model. You don't have the limitation in terms of your optimization algorithm or the your parameterization. You basically let's say you can optimize this loss function exactly. And you can optimize this also exactly. Okay. So you can get an optimal policy. So the question is, Can I? So the idea of DPO is that can I remove reward function from this? Can I combine these two equations in certain way such that the reward function gets removed? That's the idea. So it's a standard problem that you must have seen several times, right? So you're trying to eliminate one variable because there you have two equations. You have two variables. You're trying to eliminate one of them. So can anybody think from looking at these equations, how can I eliminate the reward function from the optimization? So so the idea is, let's look at the relationship between this optimal policy and the reward function. In the assuming you can learn arbitrary reward function and arbitrary policy. You're not limited by the optimization algorithm or the parameterization. Then in that case, how does your optimal policy looks like in terms of your optimal reward function? Okay, so how would you get the optimal policy? You have this objective. Is everybody familiar with this objective? This is your regularized reward maximization objective of policy gradient of PPO. Objective. So how do you maximize this quantity? The first thing would be to define a Lagrangian. So you want to optimize this over pi y given x. So you define this Lagrangian L pi comma lambda as this quantity minus beta kl pi y given x plus lambda times constraint. And now what will you do? Differentiate this with respect to pi. So let's differentiate with respect to specific value of pi. Let's say y naught given x, not overall pi. Let's say we want to do it for a specific pi, and set it equal to 0. Okay, that's what we will do in the next slide. So let's expand this expectation that we have. So what is this L pi comma lambda? This is given by summation over y belong to y pi y given x into r star x comma y minus summation y. KL divergence can also be expanded. Now gradient of this Lagrangian with respect to pi y naught given x would be, so differentiate this quantity. So only pi y naught given x. This is a linear function of pi naught given x, and so what you will get here is r star x comma y naught. And what about this? So you can try differentiating this. It will come out to be 1 plus log of pi y naught given x and we know at the optimal policy at the optimal value of pi star, this quantity should be 0, right? So we know gradient of pi star y naught given x should be equal to 0. What does this mean? This means that r star x comma y naught, and this should be lambda also, right? Lambda summation over y. This is a Lagrange because it's a Lagrange, right? Okay. So then there will be lambda here also, and so this will be r star x minus 1 plus log pi star y not given x over pi ref x lambda this equal to 0. Is this fine? So yeah. So now there are two ways I can write this equation. I can write r star in terms of pi star or pi star in terms of r star. Let me write pi star in terms of r star. What will it look like? So let's go back to the previous equation. We have r star x y naught plus lambda minus 1 so this should be bracket, yeah, is equal to log of pi star y naught given x over pi ref of y naught given x. Is this fine? I've just rearranged the terms and exponentiate this both sides. You will get e to the power. So lambda is a constant, right? So I will just put lambda minus 1 as lambda bar for now. E to the power r star x comma y naught plus lambda bar. Okay. And if you exponentiate this part, this becomes pi star of y naught given x over pi ref y naught given x. And this gives you pi star y naught given x is equal to pi ref of y naught given x times exponentiated reward function r star of y naught. So I've expressed my optimal policy in terms of the optimal reward function that is there. Okay. Now how to get this lambda bar? How do I remove this lambda bar? Anybody? We had a constraint in the beginning, right? That pi star should sum up to 1, right? So if you use that condition, so since pi star is a probability distribution, it should sum up to 1 over all the outputs. If you put this condition here, what you will get is what will you get? What does this mean? Summation over y belong to y pi ref y given x exponential of r star x comma y plus lambda bar should be equal to 1. Lambda bar, this exponential of lambda bar does not depend here, so this comes out to be exponential of lambda bar equal to 1 over summation y pi ref y given x times the reward function. Basically, it's the normalization constant. That's it. Okay. So now what does your distribution look like? It's basically pi ref. The optimal policy is base policy times some function of the reward function. Is it fine? Okay. Now I can okay. I think it would be good to have one more slide so that we can. Okay. So let me add the final equations that we have. Pi star y given x is pi ref y given x exponential r star xy over normalization constant. Okay, this is how you can write it. And I can now the other way can I express r star in terms of pi star? If you try to write it another way, this becomes Actually, you can get the other direction from this itself. So from here itself, you can get the other direction. How can you expect R star in terms of pi star? So let me copy this over there. R star x y naught plus lambda bar equal to log pi star y naught given x over pi ref y naught given x. In other words, R star x comma y naught equal to this minus lambda bar, and lambda bar is log of the normalization constant. The way we defined our z is lambda bar is simply the log of the normalization constant. Oops. So we have two equations now. The reward, the optimal reward can be written as in terms of the optimal policy as follows, and the optimal policy can be written in terms of the optimal reward like this. Both can be expressed as a function of each other. These are the two important functions, remember. So why are we doing all this? What is our purpose? Why did we write the optimal reward in terms of the optimal policy? Remember, we have two equations. One for the optimization of the reward function, for getting the optimal reward function, and another equation for getting the optimal policy. And what we want to do is we want to remove this intermediate step of learning an optimal reward function. And the way we will achieve this is by defining the optimal reward function in terms of the optimal policy. And we will replace it back in our reward maximization algorithm, which is the next step. So let's parameterize everything. So till now we were working with optimal policy and optimal reward. We said that the optimal reward function can be described as a function of the optimal policy, but now I want to learn this reward function, right? I don't have an optimal reward function. My whole job is to learn this optimal reward function, optimal policy, and everything. So how do I do this? So the idea of the DPO paper, the main idea of the DPO paper was, can we write the parameterized reward function as a function of the parameterized policy? So we know that the optimal reward function can be expressed in terms of the policy as shown here. But can I define non-optimal reward function, that one reward function that I am training, as a function of my policy, which is also not optimal? So this constrains the reward function. You are not learning an arbitrary reward function anymore. So this is what DPO assumes. DPO assumes that any reward function can be that DPO cares about can be written in this form. So the DPO assumes that your reward function can be written in terms of your parametric policy like this, and then you train this reward function that you have on top of the preference pairs. We'll see that in the next slide. But does anybody have any questions about this? That why can we write my reward function in this form? I mean, this may be slightly counterintuitive, that why have we defined our reward function like this, right? So that the previous slide just showed that the optimal policy and optimal reward function had this relationship. But now we are saying that even while training, we will assume that my reward function and policy relates like that. I will define my reward function in terms of policy, and then what will I do? Then where I was training the reward function optimization algorithm, I will put this equation over there. That's the whole idea. Okay. Okay, so this is how we will train. We'll get a pair of human preferences y plus and y minus for the prompt x, and then we'll compute reward of the positive output, which is so what is the reward of the positive output according to our new definition of the reward function? Is beta times log log ratio of probabilities. Okay, we'll call this as log ratio of probabilities. Okay, minus a normalization constant which depends only on x and not on y. Similarly, reward of the negative output can be expressed as the log ratio of probabilities minus same normalization constant. See, these two quantities are equal, right? And the training objective now, where the training objective for the reward function, if you remember, was, does anybody remember what the training objective for the reward function was? It was log sigmoid difference between reward, right? That's what we're optimizing. And we'll use the same training objective, but with this new parameterization of the reward function. So let's replace the new reward function values that we got into our training objective. Okay. This is the Bradley-Terry log likelihood. Yes. So everything is, the objective is same. We kept the same equations. We just eliminated reward function, the learning. Yeah. So what would be the training objective? Let's replace it now. Let's do it for 1x, y plus and y minus. Okay. So this will be log sigmoid rx y plus minus rx y minus, which is equal to log sigmoid. What are your rx y plus? It's beta times log ratio of probabilities. Log pi theta. So let me call it theta. So because we are training on theta. Y plus given x over the reference model probabilities minus the normalization constant minus beta log. This is your reward for the positive output, and similarly you have reward for the negative output. X minus log Vx theta. So is there something that we can cancel out here? Yeah. The log z term can be cancelled out. And what does this give me? Log sigma beta times log pi theta y plus given x and if you want you can also write it like this. This sigmoid times beta becomes a softmax. Beta times log pi theta y plus given x over pi ref y plus given x upon same quantity exponential of beta log pi theta y plus given x. Plus beta log so I've just expressed oh sorry did I do a mistake? No, this is fine, right? So I just opened the sigmoid function, that's it. So you can express it like this also. So effectively what is it doing? If you look at this objective, does it remind you of any loss function that we use? Yeah, it reminds us of softmax, right? Where these quantities, the quantity inside the exponential, these look like the logits. These are the logits of y plus, this is the logit of y plus, and this is the logit of y minus. So for input, if you have two outputs, all you do is compute the logit for each of the output, and increase the logics, increase the probability of the correct output, and decrease the probability of the negative output. That's all it's doing. It's a very simple loss function, and it's very intuitive loss function. But there's a difference with respect to when we use softmax, when you use this multi-class classification compared to when what we are using here. There's a difference. Can we think what the difference is here is with compared to what we use in multi-class classification or binary class classification? So the primary difference, there are actually two different. One is the way we are computing the logics here. Okay, that's an obvious difference, that we are using the probability of the model and the probability of the output under the policy and the reference model to compute the logic. That's one difference. But another difference to remember here is that y plus and y minus are not the only outputs possible here. Actually, the output space is very large. It's intractable. And but we are in our loss function, we are defining only using y plus and y minus. It has its advantages that now this objective is very easy to compute, but it will have its disadvantage that we will discuss. But is this fine for everybody? The softmax over the positive output and the negative outputs. Okay. So let's look. This is how it looks like. You have an input prompt. You have a positive output and a negative output that comes from human preferences, or it might also be an AI preference. Okay. Then you compute the probability of the model under the current policy. You compute the probability of the output, both the outputs under the current policy, computing the probability of both the outputs under your reference policy, and compute your the reward function, the log ratio of probabilities as your reward. And then just apply your loss function that you use for training rewards. That's the idea. And we have completely eliminated the task of learning a intermediate reward function. So, so we have already interpreted the objective. But why? What is the role of this PyRef? If you think, I mean, if you have to do it without coming through all this process, you won't have a PyRef, right? What you will do is you will compute the probability of that the model gets to this positive output and the probability that the model gets to this negative output, and just apply softmax on top of this. Why do we need this PyRef? One of the reasons that I have not mentioned here why we use PyRef is because these sequences that you generate, right? They can have variable length. Okay, so sequences that are very long will have very low probabilities, and sequences that are small will have very high probabilities. What this PyRef does is actually removes, it takes care of the length. It says that, okay, if it is a long output, even the reference model will give very low probability. So this ratio will become reasonable. So the ratio, irrespective of the length, this ratio will be a reasonable quantity. So that's one intuitive reason why dividing by PyRef helps practically. But that's one practical reason of why it helps. Okay, if you don't divide by PyRef, you will either end up with very long outputs or very short outputs, depending on how you compute this probability. Okay, so that's one reason. But another reason is that if you remember why this PyRef comes into the picture, it comes because we had a KL divergence term in our policy gradient, right? And the purpose of PyRef in policy gradient was to keep the policy close to your reference policy. You don't want to deviate too much, and that purpose is served somewhat here also. So if you look at, so let's say there is an output for which the model assigns there is a positive output y plus, and the model already assigns high probability to it. So in order to increase this quantity, what will the model have to do? It will have to, let's say it was assigning earlier 0.8, the model can increase the probability to 0.9. Okay, but if it was an output that the model assigned lower probability earlier, say 0.1, then even a small increase in the probability is enough for it to give the same ratio. So 0.9 by 0.8 is approximately equal to 0.11 by 0.1, approximately, right? So that means that if the model assigned low probability, then even a slight increase for the model is fine. So effectively, the model is not drastically changing the probability, or it can still change, but uh, we are we are hoping that the model will not drastically change the probability of the of the output compared to what the reference model assigned. Okay, it will still keep it close to the reference model's probability. Although in reality, this does not always happen perfectly, which we will see next. Okay, second thing, what is beta? Uh, so here, if beta is high, what will happen? If you think in this objective, if let's say this beta is very high, let's say 100, then what will happen in that case? Uh, the model will try to make this far away from this quantity as much as possible. It will try to increase the gap by a lot, right? If beta is small, the model will be okay to keep these values small. So beta sort of plays the role, uh, sort of plays the role of a learning rate also. It's how much weight that you want to give during training. Okay, so generally it's kept around. So depending on the length of your outputs, it will be somewhere around between 0.3 to 0.003 actually. You can, depending on how big your lengths are. So it's a huge range, and you'll have to find the optimal beta for your purpose that makes the model train. Okay, so we have seen PPO, we have seen DPO, and which one is better? It's still not clear. No, DPO has its own set of problems. PPO, the issue with PPO is implementing it. It's challenging, right? You have to learn a reward function. You have to define a value function. You have to clip the importance weight so that the grade policy does not deviate too much. And you need to do a lot of stuff in order to make PPO work. If you don't do all that stuff, there's no guarantee that it will even converge anywhere. DPO is simpler, right? You don't have to learn a reward function, don't have to learn a value function. You just compute the probability of the positive output, probability of the negative output under both current policy and reference policy, and apply your Bradley-Terry loss, right? But the problem with DPO is that its objective function, as I mentioned earlier, it does not try to look at all possible output space. It's just, if you look at, let's go back to the previous equation that we had. Yeah. So if you look at the denominator of the last expression, the denominator only has the positive and the negative output. It doesn't care about what the output distribution actually looks like. And why is this a problem? The model can actually make this quantity pi theta y minus to be 0. And if this quantity pi theta y minus becomes 0, log of pi theta y minus will become minus infinity, exponential of that quantity will be 0, and this whole quantity will reach its maximum. So the model can simply assign 0 probability to the negative output and give and suddenly the objective will be optimum. And we will see why this is a problem. So let's look at that, why this becomes a problem. So PPO, what people have observed with PPO is that many of the reward functions that we use for training PPO, they have a length bias. They prefer outputs of longer length than shorter length. And when you do PPO training with such reward functions, you will automatically get very long outputs from the policy. Okay. Okay. So why is DPO biased? So this is your DPO loss function. Now let's assume that the reference model assigns equal probability initially to both y plus and y minus. Both the outputs have equal probability, and there is some nonsensical output the whose probability is 0. Okay, so ideally, what would you want? That this nonsensical output, since it is anyway has 0 probability, its probability should not increase, right? Probability should remain at 0, which is what PPO would do, but DPO would not do that. Let's see why DPO would not do that. So initially, when you start training, your model will be exactly same as PyRef. It will assign the same probability: 0.5 to the positive, 0.5 to the negative, and 0 to the output, the out of distribution output. Okay. Now you start training. After some steps of training, either what will happen? Either this can go up, or this has to go down. Right? Something has to happen in order for this loss for this objective to increase. So if the first quantity increases, let's say this ratio of probabilities, if this quantity increases, then there is no issue, because if let's say this become 0.5 to 0.6, and this quantity remains same, or this quantity, then this will also probably decrease to 0.4, and that probably the sequence will still have zero probability. The issue is when this the negative output, the rejected output, that output's probability start decreasing. So when its probability start decreasing, what would happen to the distribution? Either that this probability will go to y plus, which is fine. If it all of that decrease, so here it decreased from 0.5 to 0.1, right? Y minus decrease 0.5 to 0.1. So if this decrease, all of it went to y plus, it is fine. But in general, what will happen is that this difference of 0.4, it will get distributed between y plus and this y naught and the other output, whatever are there. It will go to a mix of both this place. So for example, in this case, this 0.4, 0.1 part went to here, so it became from 0.5 to 0.6, and this became from 0 to 0.3. So an output whose probability was 0 initially, it was completely non-sequential output. By DPO training, its probability will become reasonable. And this happens very often when we do DPO training, that if you let's say continue training for some time, very nonsensical outputs will start emerging in DPO training. Is there any question about this? Why the problem with DPO? Generally, people will have some validation data to stop training early enough.
Can you just repeat why this?
Right. So if the probability of the negative output decrease, ideally we want that, right? Probability of the negative output should decrease. But the question is, where should that probability go to? If it goes to the positive output, see, because your loss is over the positive and negative output only. So if that all the probability of the decrease in probability of negative output goes to the positive output, then there is no issue, because you are comparing these two and that's what you want. But that's what doesn't happen. What will happen is that model does not have any way to control this. The probability will, some of it will flow to the positive output, some of it might flow to an output which was not there in the loss at all, because the loss did not say that don't generate this y naught output ever, right? So it might still end up giving some probability to y naught output, so that the probability of this y naught, this nonsensical sequence, increases, and that is the problem. Okay. So how to deal with out of distribution bias? This is also called as out of distribution bias. What you mentioned, that outputs that are out of distribution, their probability also increases. So one possible solution is online DPO. So in online DPO, it's similar to PPO. So basically, you learn a reward function here, or you assume that you are given a reward function, and you generate outputs y1, y2, and get them. So this is your reward function, LLM annotator. This is your reward model. You can think of this as a reward model. Okay. You generate outputs y1, y2, and or this can also be a human being. Show it to the reward model, and the reward model says, okay, y1 was a better output for this input compared to y2, and now you apply DPO on top of it. Again generate, again get them labeled by the reward model, and then again apply DPO. So you repeat this DPO iteratively. And what is the advantage here of repeating iteratively? So let's say that the probability of this the increased at some point, a probability of some weird sequence increased, then what will happen? That you will end up sampling this weird sequence, because this probability increase, you will end up sampling at some point. And now the LLM annotator will clearly say, no, don't repeat tokens. Repeating tokens is a bad idea. It will immediately give a negative reward to those sequences in which tokens start repeating, and immediately your model will learn to forget. So whatever bad outputs that get generated by DPO are getting fed to DPO as negative samples, and because of which it will forget those bad outputs. So it's the reward model here is working like an adversary to the DPO policy objective. DPO policy objective may encourage bad outputs, but immediately the reward model will start discouraging them. So there some kind of balance is restored between the policy training and reward model. And you have to make sure that you resample frequently. so that anytime such an bad output emerges from the policy, immediately you can suppress them, suppress those output by giving them negative reward. So this is an online setting, right? You are showing samples that get generated from the policy, and then labeling them using reward model. But what if I have preferences available, human preferences available? Can I use them to train the policy without getting into this out of distribution bias? This is something that I would encourage everybody to think about. That how would you deal with this out of distribution bias in an offline setting? This is an open question, and we don't have any answer. It's an interesting problem to think of. Is there any question about this slide? Okay, so this online DPO actually works quite well compared to offline DPO on a range of tasks. This is TLDR, helpfulness, and harmlessness. These are anthropic tasks. Anthropic. And as you can see, online DPO performs much better than offline DPO in almost all the cases. So what are the main takeaways from here? DPO can learn a reward model with learn a policy without intermediate reward model or a value function, but it can be biased towards out of distribution samples. To prevent bias, you can optionally learn a reward model and then sample frequently from the policy and rank them using the reward model. Okay. All right.